Hello everyone, my name is Daniel Dimov and today I will speak about the accuracy of GNSS, what we can expect from it and what we need in paragliding and hang gliding. To understand better this talk, you will need some basic knowledge about how global positioning systems work, and I will advise you to read something or watch some video on this topic before you continue. Okay, let's see what is accuracy and how we measure it. But first, something about one mistake many people make. They see DOP on their screens and they think this is the accuracy, but actually it's not. DOP stands for delusion of precision, and it's a ratio between user range errors and position errors resulting from this. It can be anywhere between 1 and maybe 20, and a lower value it's better for accuracy, but actually the accuracy is multiples of this value, not the actual accuracy. Most of the times it is given in meters CEP. CEP stands for circular error probable, and it is the smallest radius centered at the true position containing 50% of the points. There is also spherical error probable, the same but in 3D, and there is also R95 and 3D R95, which is the same but with 95% confidence. To measure these values, we cannot use only the receiver in question. We must use something else to compare with something else which is much more accurate than the one we are testing. These receivers are usually survey grade instruments and they are accurate in centimeters or sometimes in millimeter ranges. Okay, let's see what are the factors contributing to all these errors. Why we have error when we receive, when we get position from a GNSS receiver. Everything starts from the satellites. Each satellite constantly transmits a ranging signal, and within this ranging signal it transmits navigational messages. The most important data in the navigational message are clock correction parameters and orbital parameters. The satellite flies through gravitational field of the Earth, which is not perfectly smooth, and it is also affected by the moon, by the sun, and by the solar wind. Also, the atomic clock is drifting in unpredictable direction by this changing gravitational field. Errors from these two factors are constantly monitored, and when they become too big, the new navigational message is uploaded to the satellite. The next contributing factor is ionospheric delay. Because the signal is refracted in the ionosphere, the actual traveling path of the signal is larger than the straight line, and this converts to a delayed signal. The good thing is that these delays are good subject for modeling and for predicting. Then we have tropospheric delay. The tropospheric delay is also a result from the signal refraction, but it's smaller because the troposphere is much thinner than the ionosphere. The tropospheric delay has two parts, dry part and wet part. Wet part contributes to maybe 10% of the tropospheric delay, and it's almost impossible to predict, but the dry part is fairly easy to predict. Another error source is the so-called multipath. Multipath is a reflected signal from buildings or from the terrain And when a receiver receives at the same time direct signal and reflected signal, it's hard for the receiver to make accurate ranging measurement. And finally, we have errors from the radio noise coming into the receiver. It contributes to approximately 1.5 meters of error. Okay, let's see what could be done to reduce all these errors. First method for reducing the errors and increasing the accuracy is real-time kinematic, or RTK. RTK was developed back in the days when selective availability was active, and it is a very simple method requiring two identical GPS receivers. One receiver is called base station and it's not moving. Other receiver is called rover and it's the moving receiver. The method requires continuous data stream of corrections between the base station and the rover. In the last few years, it became more popular, so-called network RTK. Network RTK doesn't require the user to have base station. They provide corrections data of a network of many base stations covering large areas, and the correction data is transported to the rover through the internet. The next option is to use more than one constellation or more than one GNSS system. Today we have 4 global systems. First one is the American, called Navstar or just GPS. Second one is Russian system called GLONASS. Third system is Galileo, the European system. And the fourth system is Chinese system called Beidou. We also have few regional systems. India has developed a constellation of 5 geosynchronous satellites, and they provide services only over the territory of India. And Japan also was developed system for their territory. They have also few geosynchronous satellites and few satellites on highly elliptical orbits. When a receiver tracks more satellites, it benefits from the increased availability and it has more data to pick from, and it can even reject some of the satellites which are at low elevation above the horizon. All this leads to better accuracy overall. All modern satellites transmit their signals at 2 different frequencies, and when those 2 signals with different frequency travel through the ionosphere, they experience different delays. When the receiver tracks both frequencies, it is capable of calculating very accurately these delays, and it can almost completely eliminate or compensate for these delays. The other good thing is that second frequency is usually much more powerful than the first one, and with longer pseudo-random sequence. Also, there are several satellite-based augmentation systems. These systems are initially developed for the civil aviation, where the reliability is very, very important. The correction data from these systems is provided through geosynchronous satellites. These satellites also provide a ranging signal, but the most important is the correction data provided with this signal. Unfortunately, these systems doesn't improve the accuracy very much, but anyway, it's an improvement. Another way to achieve better accuracy is with precise point positioning method. This method was initially developed as a post-processing method. Um, it is working like this. The receiver records raw measurements. These are pseudo ranges and carrier phases from each satellite. And then, when they have precise orbits and precise clock corrections, they are able to calculate much more accurate position. And this method proved itself to be very good. So the companies decided to use it in real time. In order to be used in real time, the receiver must have the precise orbits and clocks. And this data is broadcasted through general purpose telecommunication satellites on geosynchronous orbits. The frequencies are very similar to allow usage of same antenna and same receiver construction. And finally, we can improve the accuracy by using some additional sensors. Uh, the good candidate for this are inertial navigation sensors and pressure sensors. Generally, the more data we have, the better it is for the accuracy. Okay, enough speaking in general. Let's see what is the situation in free flying. First, I want to show you one chart from a test flight I made. Here in green you can see the actual altitude. In blue is the altitude from a general purpose receiver, and in red is the altitude from a receiver designed for boats. It's very easy to see that the boat receiver averages its altitude in the last 60 seconds, while the general purpose receiver doesn't do any post-processing of the altitude. That's why it's a good idea to always use receivers made for flying, either general purpose receivers or receivers for aviation. With the next two slides, I want to show you how the new technologies penetrate into the mass market, and also how these new technologies come in our instruments for paragliding and hang gliding. By the term mass market, I mean receivers costs less than €100 and using either patch antenna or monopole, dipole and helix antennas. You can see that before year 2010 we had only single system receivers. Those was receivers supporting only GPS. And then with the years, dual system became popular. Those are receivers supporting GPS and GLONASS or GPS and Galileo. And now we have predominantly multi-system receivers, receivers that support three or all four systems. And recently, and very slowly, we are still in the beginning of the penetration of multi-frequency receivers. But let's see what is the situation in our flying instruments. You can see from the chart that we are still using predominantly single system receivers, and only the last year the number of dual and multi-system receivers was more than old single system receivers. It's visible that we are at least 5 years behind the main trend. Okay, let's see what accuracy can be expected from different receiver types in different conditions. I choose 4 different conditions. First is high altitude and open sky. So there is nothing obstructing the satellites in view and there is nothing nearby to reflect the signal. Second situation is at low altitude, lower than the mountains nearby, but the mountains are covered with trees and other type of vegetation. So the plants absorb some of the signal, and the multipath effect in this situation is will be almost negligible. The third situation is also at low altitude, close to the mountains, but this time the mountains are not covered with any vegetation. The rocky mountains are reflecting the signal, and in this situation the multipath effect will be significant and will contribute to the lower overall accuracy. And the fourth situation is also at low altitude, but this time the mountains are from both sides. The receiver in this situation will be in deep valley or deep canyon with obstructed view from two of the sides, and also with moderate multipath effect. Okay, but what is acceptable for free flying and for free flying competitions? My personal opinion on this is it should not be much smaller than the dimensions of our glider, and also it shouldn't be much larger than the distance we can travel normally in 1 second. And again, my personal opinion on this is that 10 to 12 meters is the optimal accepted accuracy level. And if we go back to the table, we can see that in these scenarios, the accuracy of those type of instruments is okay, and in this is not okay. It's not enough. Only the multi-system and dual frequency receiver covers all the cases, all the scenarios we can be in competition flying. Okay, time for conclusions. Are we ready for high altitude cylinder lower limits? I think definitely yes, we are ready, because even our least accurate instruments are quite okay in this situation. But we are not ready yet for low altitude cylinder limits. The cylinder limits that can be used on end of speed section or on the goal. And what we can do about all this? As pilots, we must start asking questions when we making decision about buying some instrument, some new instrument. We must have the information how accurate is it, what antenna is inside, what are the test flights, how it performed, and so on and so on. As a sport governing body, first of all, we must have information. Information about what is the current situation with the accuracy, what instruments uses what GNSS receiver, what antenna, and so on. Then we must discuss and find some working incentives towards having more accurate receivers in our instruments. And finally, if we need accuracies lower than 10 meters in all conditions all the time, we must go for receivers with L-band corrections. That's all. Thanks for your time.